Hi, as we have discussed in the theoretical section, one of the application and basically one of the reasons why depth-first search came to be is the so-called maze solver, or how to find the way out of a maze. So in this application we are going to store the map in a text file, so in a .txt file, and whenever there's a 1, it refers to a wall, and of course a wall is going to block us. The 2 is going to refer to the starting point, and the 3 is going to refer to the exit. So we start here and we would like to find the 3. Whenever there's a 1, it is a wall. Whenever it is a 0, it is the path. In this situation we are able to find the exit. We just have to go to the right. Then we have to go down. Anyways, we are not able to go to the right because there's a wall. We are not able to go upward because there's a wall too, so we have to go down. We are not able to go to the right because there's a wall. We are not able to go to the left because there's a wall. We can choose whether to go back or go down again. We can go down, and again we can turn to the right. There's the exit. We can turn to the left, but there's a wall, so we are not able to go there, and we are not able to go down neither because there's a wall too. So this is how it works. We are going to encode the map with 1s, 0s, a single 2 and a single 3 integer. Okay, so basically we will have a maze solver that's going to contain the depth-first search related code. We will have the file reader with which we are going to process this .txt file, and we have an application from where we are going to test. Okay, so the file reader is basically going to read a map, and the map is a 2-dimensional integer array. We are going to store 2 dimensions, of course. It is quite intuitive. We have to store 1 dimension for the rows and 1 dimension for the columns. Okay, then of course we will have the file name. We have to specify, we have the number of rows, the number of columns. We will have the start position for the column and the start position for the row, because we are going to decide that, okay, from where we are going to start our depth-first search, and basically it is the 2. So we have the file name, the number of rows and number of columns in the text file. So these are the text file related informations. So we are going to instantiate the 2-dimensional array accordingly. We are going to create as many rows as we have specified and as many columns as we have specified. Then we are going to create a scanner. With the help of the scanner, we have to specify that we would like to read the file with the given file name, and the scanner is able to scan the integer on a 1-by-1 basis. So 1, then the next integer, next integer, next integer, and so on, line by line. Okay, so we iterate through basically the number of rows, and there will be a nested for loop. We iterate through the number of columns, and we are going to store the next integer in this 2-dimensional array. So basically we read the content of the file 1 by 1, and we know that it is going to contain integers, so that's why we are able to create an integer 2-dimensional array. And we are looking for the starting position. So whenever the map at the index I and the column index j is equal to 2, it means that the 2 is the starting position. We are going to store the start position column index and the start position row index. Of course, we have to close the scanner after we have done this text processing. And of course, we have some getters for the position column and position row. And of course, some getter for getting the map, this 2-dimensional integer array that's going to store the information we store in this text file. Okay, what about the application? The application is going to create a file reader. We have to specify that, for example, on my computer, I store this txt file on the user desktop map.txt, and we have 5 rows and 5 columns. That's why we have to specify it. Then of course we have to parse the file. This is the file we have been specifying, that we have to import basically all the information from the txt file. Then we are going to create a maze solver with the map. So this is the 2-dimensional array, the starting position for the row index and the column index, and we try to find a way out. So what about the maze solver? The maze solver is going to store the reference for this two-dimensional map. We are going to have this boolean visited to be able to track what positions can we visit and what are the forbidden positions. You may pose the questions that, okay, are there any forbidden positions? Of course there are. If the map contains a 1, it means that there's a wall and we are not able to go there. So basically it is a forbidden position. Okay, so the find way out is going to have a try-catch block. Whenever we find the exit, we are going to throw a new runtime exception. It is common in depth-first search or backtracking algorithm implementations. This is how we notify that we find a given solution. Here, we find the exit from the maze. Anyways, we are going to call this depth-first search with the start position row index, start position column index. What will be the start position? Of course, this is the 2, so that's why we have to process the file. Okay. So this depth-first search, first of all, is going to print out that what row index and column index are we visiting. If the maze map row index column index is equal to 3, it means that we find a solution. So we throw a new runtime exception and it's going to be printed out. Okay, and basically the 3 means that this is the exit. This is how we specify it. Okay. We can specify the end of the map, which is the maze map length -1. Why -1? Because indices starts at 0. Okay, and anyways, we have to specify the constraints. If it has been already visited, we just keep it. So if we have already visited, for example, we keep visiting the 2, then the 0, 0. In my implementation, we are not able to backtrack to the previous position. So that's why if we have visited that given position, we return. If we are out of the map as far as the row index is concerned or the column index is concerned, of course we return. We are not going to consider, for example, this position because it's out of the map. Okay. And basically, if it is a wall, we cannot go in that direction. So this is the last constraint. So if we have visited that given position, we return. If we are outside the map as far as the row index is concerned, we return. If we are outside the map as the column index is concerned, we return. And if there's a wall, which means that the maze map contains a 1, why? Because this is how we specify it in this file. The 1 stands for a wall. We return. Else, it means that we are on a valid position. So this visited row index column index is true, so we set the current position to be visited. And here's the depth-first search part. Basically, this is the core of the algorithm. We have 4 scenarios. We can consider the position below, so we can go down. We can consider the position to the right, so we can go to the right. We can consider the position to the left, so we can go to the left. And we can consider the position in the upper region, so we can go up. And because I have implemented this order, so going down, then go right, then left, and then up, it means that we prefer going down. If we can go down, we will go down. If we are not able to go down, then we pose the question that is it possible to go to the right? If it's possible, then we go to the right. If it's not possible, so it's not possible to go down and go to the right, then we go to the left. Okay, if it's possible to go to the left, we go to the left. If it's not possible, why is it not possible? Because, for example, it is out of the map. Or is it visited already? Or there's a wall. So if we are not able to go down, go right, go to the left, then we are going up. So you may come to the conclusion that, yeah, basically I favor going down, then favor going right. So I prefer going right than going left. I prefer going down, going right, going left than going up. Okay. So basically this is the map. We have the starting point, the 2, we have the exit, and we are able to find a feasible solution. We just have to go to the right, then down, down, and to the right. Let's see whether it's working fine. I'm going to run the application. Okay, there's a route find to the exit. And basically this is how you can track how the algorithm works. So what positions we are visiting. The I is the row index, the J is the column index. This is the starting point, the 1, 1. 1, 1. Okay, indices starts at 0, get used to it, but anyways, this is the starting point, and the AND is the 3, 3. Whenever we are standing at the 3, 3, it means that we throw a new runtime exception, because if this is true, and we print out that there's a root. What if I'm going to block the exit with a wall, like this? There's not going to be a feasible solution, so I'm going to run the application. No solution found. All the possibilities have been considered, and our maze solving algorithm came to the conclusion that it's not able to reach the number 3 from number 2 because there are wall blocking the exit. Okay, let's try to consider some much more difficult map, for example like this, and one, I'm going to copy and paste it like this. Okay, and I'm going to copy 2 rows. Okay, and for example, let's start from here. So it's going to be the 2, and for example, we will have the 3 something like, sorry, not like that, 0, 0, 0, for example, here. Okay, I'm going to have a 1 like here. I'm going to get rid of this 3 and this 2. And let's see whether our algorithm is going to work fine or not. In this situation, we have 1, 2, 3, 4, 5, 6, 7 columns and 1, 2, 3, 4, 5, 6, 7 rows. So we have to modify the application when we specify that we have 7 rows and 7 columns. Okay, and sorry for that, I made a mistake. It was a good idea to test it on a larger map, because in the application, if you hover your mouse over the maze solver, it's waiting for a 2-dimensional integer array, the map, then the column index, and then the row index. So we have to specify the column index first. So I'm going to get the column index first and then the row index, and that's why there have been some issues. But after changing that, okay, then you may pose a question that it is working fine so far. It is working fine because we were starting at a quite symmetric position when both the column index and the row index was 1. So it doesn't matter whether we specify the column index and the row index. But okay, we have to be consistent, of course. So in this case, as you can see, we have to go down, then to the left, 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 then down, down, then to the right. And in this situation, for example, it's going to be a feasible solution, so we are able to find the exit. Let's check it. Okay, so route found to the exit, so it's working fine. What about if we block, for example, this with a wall, so with 1, and save it, then depth first search is not going to be able to find a good solution. So basically, this is how a maze solver works. And the core of the algorithm is this depth first search. We would like to try go down, then going to the right, then going to the left, and going to the up. Feel free to vary this order. I mean, if you want to go to the right first and then going down, so you would like to change your preference, then you just have to copy and paste it like this. In this case, you are going to prefer going to the right, and whenever you are not able to go to the right, then you are going down. Okay, there may be a wall, then you go to the left or go up. Okay, so sorry for that mistake. You have to change this position, so make sure that you specify the column index and the row index as we have specified in the maze solver. Start position column, start position row. I'm going to change it because usually we specify the row index and then the column index. I don't know why, but if you are dealing with Vaadin or Swing, then the first is always the row, and then we have to specify the column index, and of course we have to specify it like the row and column. Okay, if I run the application, it shouldn't. Okay, no solution, fine, so it's working fine. Thanks for watching.